Okay, so we're going to be moving on to RL circuits just after doing this final inductance question over here. It's asking for the maximum potential difference. So E equals negative L I over T. L I'm given, I is here and T is here in milliseconds. That's millihenries in milliseconds. So that milli here, they will actually just cancel each other out. So I can ignore the millis. What I need to do is find the EMF, but where? I have a bunch of slopes here. There's a slope. If you remember from the previous questions in the last video, I over T becomes a slope. Well, that's zero, so nothing happens there. I want maximum magnitude. So I have this, 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 and this to choose from. These are my induced EMFs. You can probably see that this is the smallest, so I highly doubt that'll be any good. I have this slope compared with this slope and compared with this slope. This is a steeper slope than this, so I can see that this one is probably going to be a lot bigger than this. Best way is to double check all the slopes, but I can see with my eyes that this is bigger. However, these two are quite close. This is a bit longer, but this seems to be kind of, turned a little. So I don't know which one's the maximum, but we're going to find out. Let's just put some numbers into this graph. I don't like this very much, so let's fix that. 2, 0, minus 2. And if that's 8, so 2, 4, 6, 8. 2, 4, 6, 8. So I'm going to start with this slope over here. I'm going to check this one. Let's see that slope, the I over T. Both of them I'm going to multiply by 10. This milli is going to cancel with this milli because this is milli, but I'm dividing by that milli. They will cancel each other out. Let's check the slope. I have, if you remember, rise over run, y2, that's a 2 by the way, y2 minus y1 is over x2 minus x1. So, oh my god, that's bad. No problem. y2 minus 4, minus 4, minus 4. Divide that by the time. We have a time of, I can see that's 2 seconds. I finished at 6, I started at 4. Minus 4 is minus 8. Divided by 2, which gives me 4 amps per second. All right, very nice. Let's check the next slope. Let's just check, because I have a funky feeling that is actually stronger than this. Most people would automatically assume this one, but I don't know. My spidey sense is tingling. Let's have a look. This starts at 2, so I'm just going to write 2 minus negative 4. 2 minus minus 4. That becomes plus. Divide that by, that is supposed to be a 4. Jeez Louise. All right, the time. The time between here and here, that's about halfway between 6 and 8, right? So that's about 7. 7 minus 6, which is 1. 7, that is not a 7. That is clearly a 6. 7 minus, so it's not a 7 either, minus 6 equals, what does that give me? So that becomes 6 divided by 1. That is 6 amps per second. See, I knew it. This is bigger than this. This is too small. So in my formula, I'm just going to take this 6, I'm going to multiply that by my 10. So I'm going to do lit. So I'm going to do 10 multiplied by, this is I over T. So 10 I over T together is 6. That gives me an answer of 60 volts. That's the answer for the first question. So let's move on to the next one over here. Where are we? Oh, what have we done? Too far. This shows an RL circuit. And you have this time constant, it's very nice, and you have, it doesn't have a time constant, but actually you don't even need it, because why? It says here, the initial current. So, what did we say about inductors in a circuit? What does it do? An inductor in a circuit will block the current at the beginning. So, what I'm going to do is ignore everything and just write 0. Job done. The current is being blocked. I don't like this blue. It doesn't look scary and angry enough. Teacher pens are supposed to be angry. It's supposed to be red. There we go. Yes, 0. The current is being blocked by the inductor. It is not allowing any current to flow. However, after a long, that's where I've seen time constant. I've seen it somewhere. T is greater than 5 tau. T is greater than 5 time constants, just in case you have forgotten. If you are showing a graph for the current maybe rising like this, at maximum, after 5 time constants, tau, the current is full, maximum current. This is maximum. So if you see something like this, you know it is maximum. The inductor, what did I say in the previous video? The inductor becomes a wire. We ignore it. All I need to do now to find the current is simply going to be I equals V over R, EMF over R. Clearly we can see the EMF, which is written here as 9, and we can have R is 50, 9 over 50, and they didn't even ask you to solve that. You've literally got 9 over 50 right there. And this question here is asking you for the time constant. So the time constant, tau, is the L over R. That's the rule for the time constant. So we're going to do L, which is my henries. I will do 2, and I'm going to divide that by my 1 mega. Mega is times 10 to the 6. Mega means million, mega million. So I remember, mega million, times 10 to the positive 6. 6 zeros. Put that in the calculator, you will get to microseconds, because that becomes -6 when you put it in the calculator, to microseconds. Micro is -6. What's happening in this question? It's saying that we have a parallel circuit, battery, an indicator. Well, clearly that's wrong. It's supposed to say inductor, so there's a little boo-boo over here. That's inductor. 2 resistors. Switch is open, no current. Which statement is true? When the circuit immediately after the switch is closed. So let's see, after the switch is closed, straight away this is blocked. Remember, inductor blocks the wire, blocks the current. The current must flow in this path. So we have a current through R2 and R1. We don't have a current through L1. So the best answer we can clearly see here is L1. No current through L1. Over here, after a long time it's closed, what is true? So I'll change the color back to blue again. Now, after a long time, this means that the current will flow through this. This becomes a normal wire. It will pass through here, it will pass through, and it has a junction. Now you need to remember something about short circuits, shorting a circuit. What does that mean? That means right now the current has a choice to pass through a resistor. And then it also has a choice to pass through no resistance, the path of 0 resistance. If you were an electron and you were sitting here, you had a choice to use up your energy if you had like a physics lesson to go to, or you can go straight back home to play your PlayStation or whatever. You're obviously not going to go through the resistor. You're just going to take the short and easy path. Just like electrons, you are lazy. Yes, so the point I'm trying to make is, if you have a wire without any resistance, the current will flow through that wire. So that means in this question, no current passes through R1. We do have a current in R2. It has to pass through the battery, through R2, and then through L1, back home again. So what can we say? The series circuit now, R2 and L1 have the same current. R1 has 0, so this one is wrong. R2 equals L1, R1 equals 0. That looks good. Let's double check. L1 and R1 are the same. R2 is 0. That's the one up here. No, because that is the same current. And then they're all equal. That's clearly wrong. So straight away we figured out the answer. It was B. Back to red. There we go. Okay, so now let's check out this one here, parallel circuit. Exactly the same kind of thing. However, now we have a resistor. And this is the same kind of question that I did in the previous video with the big table. The one that if you understand that, you should understand all of them. This is the same kind of circuit as that. So what this is saying, after the switch is closed, initial current at the beginning. Well, there is going to be a current. Yes, this one's blocked. There is no current in this part, but there is still a current. Why? Because it can still pass through here. We have a current in R3 and R1, but nothing in R2 and L1 is blocked by this at the beginning. So this is wrong. No current through R1, that is wrong. No current through R2, yes, that is good. R3, well, we already know it's wrong, because the current will flow through it. After a long time, let's just say, I'm going to add this little bit in here for you. After a long time, or when the switch is open or whatever, just after a long time, infinite time, 5 tau, then what happens? Then this becomes a normal wire, doesn't it? Current can flow here, but it will not skip R1 this time like in the previous question. If you look at the previous question, it skipped through R1. Look at that. Why? Because there was no resistance in this path. Over here, there is a resistor. So this will turn into a simple parallel circuit. Current will flow down this way and through this way. So this is a parallel section of a mixed circuit. Very nice. So let's move on. When the switch in this circuit below is closed, what will happen? Originally, well, there will be no current at the beginning, but that's not the full story though, is it? The current will slowly rise to a value of whatever that formula is supposed to be. Okay. Then you have the current gradually rising to V over R in the direction shown, and the current will start at V and R, then drop to 0. Okay, well, these are all terrible, apart from this one. No current will flow is wrong, because yes, initially no, but after time it will. Why? Because we have a graph. It goes up like that, doesn't it? And remember I said earlier, this is I max, the maximum current. To find the I max, of course, is V over R. That's the formula to find the voltage. It will gradually, slowly, rise to V over R. That's the best answer. Over here, a circuit is composed of this battery, this inductor. Oh, that's nice. They managed to spell inductor correctly this time. That's good. I like it. What are we doing now? We're trying to find the energy stored in this inductor. So if we want to find the energy stored, U equals a half Li squared. Well, small problem here. We don't have I, do we? Well, we can figure out I. We can do I equals V over R. Why did I write? Oh, no, I did. There's R. 12 over 6, which is 2 amps. There we go. Now I know what the maximum current could be. Let's now multiply that by my half L. Where's my L? 5 henries is there as well. 5, multiply that by 2 squared. 2 squared is 4. 4 times 5 is 20. Half of 20 is, of course, 10. Very good. All right, so we're getting through, almost done with this page, and we will be finished. What's happening over here? Let's see. Oh, I don't remember this one. I remember. A lot of people had problems with this one. Let's have a look at what's happening. You have a current flowing this way, and this says just after the switch is closed. So initially, inductor blocking the current in its path, and look at that. It is a simple series circuit, which means all of the current is blocked. 0 amps will follow. This is the least. 1 is the smallest. Something else might also be 1, but 0, sorry. But let's find out. Over here, what's going on? Blocked. No problem. But we have a circuit this way. What does that mean? That's I equals V over R. Let's assume everything is set to 1. I'll do 1 over 1. Let's just call it 1. Okay, so 0 amps, a fake 1 amp. Obviously, I just made the numbers up, but I'm comparing the values. I'm comparing them. Here, blocked. Very nice, blocked. But what does that mean? That means the current can flow here. And in this series circuit, I have 2 resistors in series. You simply add them. So I will do I equals V over R. I'll keep the V as 1, but we'll divide that by 2R. That becomes a half. So 1 is the smallest, followed by 3, followed by 2. 1 followed by 3 followed by 2. This means smaller than. There's a little way to remember it. It's something like a big shark or a small shark. That looks exactly the same. Something about sharks, I don't know. One of my students was telling me, and I thought that was a good way to remember. So just remember, to the left it means smaller than. To the right it actually means greater than. It can come either way in your exam. And that is the final multiple choice question for this topic. Thank you very much.